record. And then share screen. Okay, first. So we first will start with some concept. Okay, so today we will start with machine learning. So the very first thing I would like to talk about is just some basic is the three different types of machine learning, okay? And today we will start with supervised learning. So that's one category. The second is unsupervised learning and the reinforcement learning. Okay, so that's the three categories that we are going to discuss. So then the first, what is supervised learning? Okay, supervised learning. So for the data, it's labeled. Okay, later on we will say, okay, regarding data, we normally have features and we have targets. Is it? So the targets is labeled, okay, and it's direct feedback, and then you can predict outcome and the future, okay. And maybe you will see all of this kind of vague, but when we look at our examples later on, you will have very clear idea, okay. But anyway, the data is labeled, okay. So generally speaking, it's a target, okay. And the under supervised learning, there is one big chunk of applications regarding classification. Okay, classification, so based on name, is it? So based on the features, generally it's based on the data's features. You can classify the data to certain category. Is it? So like we all know, okay, animals, is it? But animal, we have lion, we have tiger, we have cats, dogs, something, is it? So each of them, they have features, is it? So just kind of like, suppose it's some images that you got the image, then you can categorize as a cat or a dog. Is that how do we identify this? Based on the data's features, okay. So that's called the classification. And classification is for discrete class labels, okay. And it can also be used for regression, okay. Regression is used for continuous value, and we will learn of those. The second type is unsupervised learning. Okay, unsupervised learning. So unsupervised, then the data is not labeled. So you don't know. Basically, you just got all of the features. Okay, you don't know, and then you need to sort them out, kind of. Then give them a classification to group them. So kind of like over here, you find a group with clustering. Okay, so no feedback. We need to find the hidden structure in data. Okay, so this is also quite useful. And later on, we will also see it can also be used for dimensionality reduction. Okay, and we will learn of those concepts. And the reinforcement learning, so it's some decision process using rewarding system. Okay, so it's devices that improve its performance based on reward. So that's just the very general idea. And here it's too simple. We will start with is perceptron and adaptive linear neurons. Okay, so the very, very basic of neural network. So today we will start with perceptron. Okay, then, so you may hear this a lot, neural network, is it? It's the one of the biggest thing in machine learning, is it? So it has the basic starting points from artificial neurons, is it? So the early history of machine learning, so what is that? So it's the neuron, we call it MCP neuron. Okay, so it's Warren and Water. So these two scientists, they first proposed this concept. Okay, we see it's a starting point, MCP neuron. So what the idea is, kind of try to mimic a nerve cell. okay, how nerve cell works. So like for all of us, is it, so we see something, is it we smell something, is it we taste something, is it, so all of those are some input signals. Is it input signal? So input signal, we take input signal, is it, and then, so it says signal arrive at some part called dendrites, is it? And then they are going to be integrated into cell body, is it? But is if the accumulated signal is that exceed certain threshold, okay, so later on we will also see certain threshold, then it will be fired and output some signal, is it? So we take some input, is it? And then we can identify, okay, we will know, okay, that's a dog or that's a cat, is it? So that's the output. So you have some input signal. And so that's just the simplest cases. We call it artificial neuron to mimic that. And then with that, it says a few years later, there's another science, Frank Rosenblatt, is it make some improvement, is it propose the first concept of perceptron, okay, the perceptron concept. So the perceptron concept, then over here is, we will say it's to learn the optimal, so the optimal weight coefficient. So we will spend a lot of time to talk about this weight. Okay, it's weight. And generally, we also have input signal. So we will identify some signal, is it? And the signal, like the previous slides showed, is it that artificial neuron, is it? So it's aggregation, is it? So it's accumulated signal. And how do you accumulate? So it's some weights on the input signal, is it? And then all of them work together. It's a kind of aggregation, is it? And then you will decide certain threshold. So this is a threshold. So if it reaches the threshold, then it will fires output signal, okay. So that's the kind of process, is it? So perceptron, so this Rosenblatt, so he first proposed how to find, so the goal is to find the optimum. To find the optimum. How do we find the optimum? It's through train and learn, is it? To find the optimal weight. Optimal weight, okay. And once you find the optimal weight, then whenever the new signal comes using the optimal weight, then you can arrive at certain results, okay. So that's the idea about perceptron, okay. So perceptron basically says is the first to propose the concept of learn the optimal weight, okay. Okay, so that's about perceptron. Then let's see, yeah. Okay, so let's come here. So here we comes the simple math background, okay, about the perceptron, the artificial neuron, okay. And here it's a simplest case, okay, because we just consider a single neuron. Okay, this single neuron. And the first concept, like I highlight on my slides, the first concept is about the decision function phi. Okay, decision function phi. So this concept functions in math, okay, regarding math. So decision function phi is regarding something. Is it, what is that something? It's some linear combination of some input values. Is it input values and the corresponding weight vector? So this Z, So Z, we call it net input. Net input. Okay, Z is the net input. And what is net input? Z basically is WIXI. Okay, X we already in the neuron, is it artificial neuron? We said it's some kind of signal, is it? And basically over here, it's some feature. We have the official name, okay. It's some feature, some feature. Is it like how long it is, how wide it is, how tall it is, the weight, the color, is it? So all of those, it's some feature. And the W is weight, the corresponding weight coefficient. Regarding that feature, okay, regarding that feature. And the feature we can collect, is it? So feature is part of the data. That's all of our thing. We say big data is you collect all sorts of data. Is it like user data? Is it then try to find some pattern? How do we find some pattern? Is to find the weight, the optimal weight, okay? And then, so this is the simplest case, is it? Because we just do linear combination, but it's not always linear combination, is it? Later on, we will say there are a lot of complicated cases, okay? But over here, we consider linear combination, okay? Linear combination, and then we call this net input, okay, net input. Then, so then you apply certain function to this net input. So phi is some function. We call it a decision function. Is it decision function? So you make a decision, and then make a decision. So how do we do that over here? The simplest case is, it says if the net input, is it if the net input Z, is it, that's our net input. So sigma WI XI. So this is regarding all of the features, is it, and their weights. Is it we multiply and we sum them together. If this greater or equal than certain threshold, so this is threshold. So if it is greater than threshold, okay, then we predict that sample is class 1. Okay, class 1. So suppose we want classification if the image is a cat or not. Is it? So based on, so you can have millions of cat pictures. Is it? You just pick one picture. Is it? Pick one picture, and that one picture has a number of features. That one picture, like each pixel color, is it a lot of features, is it? So that's just one feature, and then times its corresponding weight. And then regarding that, you will decide if it's greater than certain threshold. Okay, if it is, then we say, oh, it's a cat. Otherwise, then it is not. Okay, so this is called perceptron algorithm. Okay, perceptron algorithm. And this decision function, we can see it's basically it's just a variant of unit step function. Okay, so it's a very simple math function called unit step function. Okay, so this is the idea. Then let's see. Let's take a look at the next slides. Okay, and then so previously, so we said this is sigma WIXI, is it? So I from 1 to certain features, M features here. Here's assuming each sample has M features. M feature. So one feature can be considered the weight. The second feature can be considered like length. The third can be considered as width. So that's called a feature, okay, feature. And so you have M feature. That's the previous slides we defined. This is called net input. Now we modify because we also consider if it's greater or equal than threshold. Is this threshold? And we want to make the case simpler, so we can move it to the left. Is it? Or we minus theta on both sides. Is it? Then you will have minus theta plus. Is it? Then over here it changes to greater or equal than 0. Is it? And with minus theta, then how about I said I define W0 as negative theta? Is it? And X0 as 1. Is it? Then I can rewrite this part as sigma I from 0 to M and Wi and Xi. Okay, but the number of features is still M. The first one, when I is 0, this is not a feature. Okay, this is just, we want to deal with that threshold, okay. And generally speaking, we call this, like over here, it's called a bias unit. Bias unit, okay, because this X0, it's not a feature. Okay, the features start at 1. Okay, start at 1, 2M. Okay, 2M. Then if we define bias, we also give bias a weight. Is it as we give the bias, and then our the decision function. This is a decision function. Phi, then we can redefine it. Say, okay, the net input Z, if it's greater or equal than 0, then we classify that sample as class 1. Otherwise, we classify it as negative 1. So that's the redefinition. Okay, so be careful here. We put the threshold as the bias unit, okay, and move it to the summation of the weight and the samples feature. Okay, so that's regarding the formal definition. So here it shows the mass diagram, okay, and so the x-axis here, so the horizontal, this represents the sigma Wixi, okay. So over here, is it over here? That's the matrix format. In math you learned, is it? That's a matrix format, is it? And if we decompose, we can rewrite like this format, okay. So anyway, basically this is Z, is it? This is Z, okay. And so you can see, okay, if this value, is it, if Z, the net input, is it, if it's greater than 0, greater or equal than 0, is it? So that's the right part, is it? Then you see this is unit step function, is it? Then it has 1, is it? It's 1. Otherwise, is it? Otherwise, then it is negative 1. Is it? So this is called unit step function. Is it unit step? Generally, when we discuss a function, we see this, is it all sorts of function? But this is kind of this is called a step function. Is it? It's a horizontal line. Is it? So, but the input, so the net input here, as it depends on if it's greater or equal than 0 or less than 0, okay. And more visualize So here it shows the visualization, is it? So we have two categories, is it? So we have the plus sign, is it, of the plus sign. So each one of this is a sample. This is one sample, is it? And this sample, how many features? It has two features, x1 and x2. Two features. The x1 and x2, is it? And then based on, you see their x and y value, very easily visually we can see they can be categorized as one class, another class, is it? Then later on, after that, then if you have another data, you will easily categorize, okay, this belongs to the right side, is it? Because the plus belongs to the plus sign class, is it? So that's the idea about, and over here it's also linear separable class, okay? Later on we will see some cannot be linear separable. Okay, then let's come back. The first machine learning, okay, algorithm. What kind of learning? Perceptron learning, okay, perceptron. The concept about perceptron learning, okay, because you see, this is a very important expression, is it? This is a net input. This is known because they are features, is it known? You collect them from data, okay? But weight, unknown. It's unknown. Is it? Because if we all know, so if we know the weights for each of the objects, then we don't need to worry. We even don't need machine learning, is it? The problem is we don't know that weight, okay? We don't know. So the goal is to find the optimal, so goal to find optimal weight. So that's the goal, is it? That's the goal. Okay, and then let's see. Because we don't know, and it's not just that easy. You can find a math formula to come up to calculate the weight, is it? So the machine learning, the only thing we have is data, a lot of data, is it? So what do? We want to find the weight, is it? So regarding perceptron, so it's at very beginning, so at the beginning, we initialize the weights to 0 or some random number, is it? Okay, so here I from 0 to n, is it? WIXI, is it? So at the beginning, you initialize them to either 0 or very close to 0. It's a very small number. So you assume something, is it? Then for each training sample, this is a training sample, okay? Be careful, this represents XI. Okay, this is regarding a training sample. So it likes we have millions of photos. We take one out, okay, take one out. So that's why this is vector representation. Is it? This is not like this. This is scalar. Okay, this is one feature. Be careful here about this mass representation. Okay, so one sample is that we represent that single sample, all of its feature as big Xi. Is it? Basically, if we decompose it, is that it has X0, I, X1I, X2I to XMI. That it has all of its features, okay? And here it's vectorization representation. So that's why over here it's bold. Okay, both. And for each of this, what are we supposed to do? We calculate the output value. Okay, y hat. Okay, y hat. So that's the first step. Okay, we calculate the output value y hat. And then we update the weights. Okay, update the weights. So let's see what all of this means. Okay. And here it says the output value is a class label you're going to predict, use that unit function. Is it that unit function? So we have input, net input, I from 0 to n, Wixi. Is it Wixi? And regarding this specific sample, is it has its x0, x0, is it I, and x1i, x2i, to xmi. Is it regarding this one sample? Is it we assume some I? Is it w0 is always this negative threshold? Is it? And the w1 is you can initialize with some very small number. Is it? And w2 maybe you just 0, and the w3 some other very small number. Is it? So you can assume that. Is it? And then you multiply each w. Is it? Each w with the corresponding x value. Is it? We can have this input. Is it? And then based on if this input is greater or equal than 0. Is it? Then you can determine the corresponding yi. Is it? Yi, if it's 1 or -1. Is it? So I add the hat. The hat, this is predicted. Is it? Okay, so based on, suppose I say, okay, this image is a cat. Is it? It's a cat. And the real one, so yi, is it yi? So real one, suppose it's a cat. And what I predicted is also a cat, so 1. Is it? So the real one is 1. And I predicted using this calculation, I also come up with 1. Is it? With 1. Okay, and then how do I update the weight? Is it? Update the weight. It is, then you can do is, this is the real value. Real value. Is it? This is predicted. Is it? So you minus both. Is it? You minus both. So that's the difference between the real and the predicted value. Is it? And you times the corresponding feature, not the corresponding sample. The sample. Is it? So that's of the input signal. Is it? Input signal. And then what you can do is you can find the corresponding weight for this adjustment. Is it? For this adjustment. And then you update the weight. Okay, you update the weight. Then you update, because this delta wj, is it? This is regarding one feature. Is it? For every feature you're going to do this. Okay, every feature. So therefore, one feature you have this, so this you calculated, then in this case it's 0, no update basically. Because here we either have 1 or -1, is it? Is it? And then for your next sample, is it? You can recalculate this, is it? So through a lot of sample, each time you update, and then you will train it, it's getting close. You predicted this y hat value getting close to the real values. If you can train it getting close, then you will find optimal W. So of the W, then it may not be those values, starting value. Is it maybe some this 0.3, this may be 0.5 something. So you will find the optimal value W. Okay, then later on, once you have this, whenever you have a feature, is it whenever you have the feature, then you can use this and that optimal weight value, then you can calculate the net input. Based on that input, you can predict your y-hat, and your y-hat will very close to your real target value, is it? So how the accuracy it is, then later on we will also see. Okay, so this is the general idea about this perceptron learning. Okay, and for perceptron learning, we just need to be careful as it must linearly separable, like over here it shows. So if you have data that's not, like in the second case and third case, both are not linear separable, is it? Then we cannot use perceptron. Okay, and if you use perceptron, the accuracy going to be very low. Okay. So that's a perceptron. And the Adeline, we will come back later. Okay, so let's go to take a look at our code. Then we may have better understanding of the perceptron, how it works. Okay, and for perceptron, over here we will write our own perceptron learning. Okay, perceptron learning. And this example I taken, so so some of our course material from this textbook, not textbook, from this book. Okay, and it's one of the best machine learning using Python. Okay, and I put the reference material there, and you can check if you want to get to the book. Anyway, so here we write our perceptron, and in Python, the Python machine learning has package, and that package also contains the perceptron. Later on, we will also see that. Okay, but here I will give you the idea how do we write our own perceptron learning. Okay. And over here, we define the perceptron, okay, as a class. So this is a Python class, okay. We don't need to worry too much. We are not going to write, okay. But anyway, this perceptron we defined as a Python class, and based on what we learned, is it what do we need? And in the slides, you remember we have that eta, is it? So that eta basically it's some learning rate, okay, learning rate. And we also have a number of iterations, okay, number, and this is overall the training data set, okay. So it depends on how many training samples you have, okay. So this is regarding samples. The learning rate, because you remember we update the weight, is it based on yi and yi hat, is it? And the learning rate and the times what? And the times that w, is it? For certain feature, is it? So this is regarding the WJ, is it? That's our goal. We keep updating, is it? For each sample, is it? You're going to do this, is it? Then you update, and you will find the delta W, is it? And then we are going to update the W, but we are going to use some learning rate, okay, learning rate. And the learning rate is that it's between 0 to 1. A value, okay, a value. And over here we also have some random number generator for the starting weight, is it? Initial weight, some random weight. Okay, so that's the general parameters, okay. And then next, let's see, over here we have W, is it? So W is some one-dimensional array, okay, it's weights. Okay, and we are also going to collect all of the arrows, and the arrows is going to be a list, okay, list. And then next, let's see. So within this perceptron class, this is in Python, this is called constructor. Okay, so Python's constructor is different from other programming language, okay, like Java, C++. Its constructor is called the init, okay, that's a constructor. So the constructor, so eta, number of iteration, random state, those are called data members, is it? Data members, or we call it instance variables, either way, okay, of the class. Is it? So anyway, it has eta, so learning rate, number of iterations, some random state. Okay, you define it. So that's the constructor parts. And then next, let's see, the fit. So this is the most important function. So the fit. Fit is to do training. Okay, do training. Okay, do training what? Via all samples. Is it via samples? Okay, so over here we have some parameter. Is it parameter x and y? So this x is what? Is some array like. Okay, array like. So what does the shape look like? So it has number of samples. Is it number of samples and the number of features? Is it? So it has like x0, is it x1, x2, is it 2xn, is it? So those are features, is it? And 1, 1, 1, 1. So this is the first sample. First sample, is it? Then you have second sample. So this is the second sample. Second sample, is it? And each of it has m features. Is it? Totally, we have how many? Over here it says n features. Okay, so this is our n. Okay, and totally how many rows of data we have? We have n samples of rows. Is it? Of rows. So the dimension of this X array, is it? Is what? Is n sample by what? By n features plus 1, is it? Okay. Supposed to be this. This is the X, is it? And what is Y? Y is the target value. So if it is a cat or not. So it's 1 or -1, is it? Corresponding to each of the sample, okay? So we call it target value, okay? Target feature, okay, so keep those terms in mind. Okay, that's the terms. And then next, let's see how we define the fit, is it? And here we use what? Here we use perceptron, is it a perceptron? Okay, so there's nothing new, as it just generates some random number, okay? And over here, this is weight. Is it weights of the weights? Is it? And the weights, we just random generate some small number, is it? You initialize. And over here, we pick some random number, then do normalization. Is it? Do normalization. So anyway, this is a weight. And this is going to be a list for error collection. Okay. And then next, let's see, over here. So let's first take a look at this loop, the inner loop. Okay. So inner loop over here, is it? We zip that feature and its target value, is it? So features and target, is it? X and Y, is it? So Xi is going to get each sample, is it? Each sample's feature. target is each sample, okay? So this loop is regarding all samples. Is it regarding all samples? Okay. And over here, how do we find? Is it, you remember what we calculate is the learning rate times learning rate times what? Yi minus Yi hat. Is it? So this is the target, Yi, and this is the predicted. Is it? How do we predict over here? You call this function predict. Is it? What it returns, it depends on your net input. Is it? So it will call this net input. How do we calculate net input? So net input Z, is it? You remember it's equal sigma I from 0 to M. Is it? Wixi. Is it? So yeah, so is it? So it's just do dot production because here we use matrix. Is it? So it do dot product. Is it? With of what? Of your feature. Is it? So this is the vector feature. Is it? And what? And your weight. Is it? So here is all of the weight. Is it of the weights? So this is a net input. Then based on if this net input is greater than 0. If it is greater than 0, it will be 1. Otherwise, it will be -1. Is it? So predict will return 1 or -1. Is it? Based on what? Based on this. So this basically, if we write as the math format, is it? Based on that, exactly, it will be x times w. Is it? So that's vector format. Okay, vector format of this. So here we decompose it in scalar format. Okay, but anyway, so here you have the predict. Is it? Predict is y hat. Is it? Y hat for each sample. Okay, for each sample. And then you're going to update the weight. So this update is at W, delta W. It's the update. Then did you see we will update of our weight. Is it? How do you update? Then you use update times the corresponding value. Is it? Okay, once you have this, then you also want to know, is it? Because in this is simplest case, if your update is 0, is it? Because we based on, so update here is this hat. This is predicted. Predict. This is real. Is it? So if it is 0, that means you predict correct, is it? And if it is not, that means you have error, is it? So that's how we come up with the error, and you add it to the error list. Okay, so this is what this feat method does inside this perceptron class, okay? And we also already looked at the net input calculation and the predictor calculation. And then next, let's see the real example, okay? So over here, our data sets, we will deal with a CSV file. Is it pandas CSV file? And we will get, it's called iris data, okay? And it at this website. So this is a very classic machine learning data repository. Okay. So this is some flower data. Okay, and it shows how many of the samples we have. We have 150 samples. Okay, sample. And what it look like? It looks something like this. Okay, so it has some data. There's some data. It may be petals, width, length, something. And this is, so this column is target. Is the flower type. flower type. Okay, so that's our original data, how it look like. So over here, this is Y, okay, and all of this are X, okay, X. Okay, that's regarding data and this drawing. So here it just shows us, okay, so we can clearly see two different type of flower is a setosa and versicolor is it a different type based on their sepal length and petal length, is it? And then next, let's see, how do we use our perceptron? And if you recall, we defined that perceptron class, is it? So we are going to create a perceptron object. And over here, the learning rate. This is learning rate. Learning rate, okay. And this is the number of iteration, okay. We are going to go through. And once we define once we create this perceptron object, then we can call the fit method fit with our data, X and Y. Is it our data? Okay, so once you have this, and then next, let's see. So then over here, is it? So this YP, is it? You get from the data frame, is it? The last column, is it? Last column is the definition of its certain type of flower, is it? And then we will decide, okay, if it is or not, is it? Then you give the value either 1 or -1, is it? And this is with the 101 sample, is it? Okay, so we can find its target value. Target value, is it? So basically it's Y101, is it? So it's either 1 or -1, is it? Based on the data we know this, is it? Okay, we can also find the corresponding feature, is it? So in this case, septa length and petal length. So we can also get, this is 150 sample feature, is it? Feature. Here we only collect a feature of what? The length and septa length and the petal length, those two features, is it? We get it. And then you can use it to predict. Is it? You can call the predict because we already trained, is it? So with that fit, is it? With that fit, we already know it's all of its maxi or optimal weight. Is it optimal weight? We already know. That's why with this specific provided samples features, we can predict this Y. So basically this predict will give us what? Will give 101's hat. Is it? So we will know the predicted value. So we can see the predicted is what? Is 1. Is it? Is 1. So it's not the setoso, it's the other type. Is it? It's the other type. And then similar here. Okay, let's see. Over here, we use what? We try from 101 to 105. So we will try to predict 5 samples. Okay, with 5 flowers. We can test our result. Is it? Same thing, we will decide if that's the certain flower, is it? And we can, from our data, is it? Because totally we have 150, is it? So we will get 101 to 105, is it? All of their lengths, is it? That septa petal length, septa length, we can get their X values, is it? Once we have, then we can predict, is it? And you can find, oh, it's all 1, is it? So it's not this setoso type, okay? So over here, this example shows us how do we do the training, and then after we do the training, then we can do the predict. Is it predict? So that's a general idea. So we get a glimpse of the idea, and we will stop.